claim that the sums S sub t form a Cauchy sequence. And what's a Cauchy sequence? See, if I can say that the S sub t's form a Cauchy sequence. The S sub t's are just sums, right? They're real numbers. So I have a Cauchy sequence of real numbers. What's the theorem that says, oh, what about that? Is there some major fact we know about Cauchy sequences of real numbers? This is a huge fact about the real numbers.
If x sub m, like absolute value of x sub n minus x.
Oh yeah, that's
the delta. Then
here. This is what you're searching for. X sub I is Cauchy if there exists if given epsilon greater than 0, there exists an n of epsilon such that whenever p and q are mutually greater than that, it implies that the absolute difference of x sub p and x sub q is less than 0. That's a Cauchy sequence.
right.
Okay, but there's something about what they do that is special with the real numbers and doesn't always happen in other number systems, like the rationals. All right, let me ask you this. Does a Cauchy sequence of rational numbers converge within the rationals?
Yeah. No. Not within a rational, no, within a real.
Yes.
Guaranteed.
Why is it guaranteed? Because the reals are Cauchy. Right? In fact, if you go find yourself a copy of Edmund Landau's book on the construction of the real number system, does anybody know what a Dedekind cut is?
Yes.
Okay. There's two ways to construct the real numbers. Dedekind cuts and then sequences of rationals that converge to the reals. If I have the sequence 1, 1.4, 1.414, 1.4142, 1.41421, 1.414213, 1.414213, okay? These are all terminating decimals, so they're all nice rational numbers. You can see that these things agree in all the initial significant digits, right? So they're getting closer and closer. This is a Cauchy sequence. If you give me an epsilon, I'll just go far enough out so that I agree in so many places that the difference is minuscule, right? Lower than your epsilon. All right. What does this converge to? The square root of 2 is not a rational number. Landau takes the entire sequence of rationals and defines it to be the square root of 2. So the real numbers are the rationals, and then we identify. Well, here you can actually phrase all numbers this way. I can have a sequence. If I want to, the rational number 2, I can just keep repeating it, right? They're all rational. These are all rational. So if I am willing to restrict myself just to rational sequences, I can represent both rational numbers and irrational numbers. So that was a very clever construction of the reals, but what you're in the back of your mind, a number is really a sequence of rationals. That's kind of hard to get your head around. 2 is just not 2. It's infinitely many 2's with commas between it. And then the square root of 2 is this thing. Right? That's huh? Yeah, it converges to that. There's always another rational. Yeah. You never step out of the rational. But it converges to this. So you build into the reals the property of completeness. Very often this is axiomatized by invoking the least upper bound axiom. So then you say, how would we define the square root of 2 using the least upper bound? The supremum of set of x such that x squared is less than 2. So if I have the least upper bound axiom available to me, I segue around the whole thing in just 2,000. See why that's the square root of 2? Anyway, my point is that the real numbers have no holes. Any Cauchy sequence converges to something. In fact, that's an if and only if. That's an if and only if. Let's prove that. Let's prove that a convergent sequence is Cauchy. Can we do that? We got enough. Anything we talk about is worthwhile. What the heck? So this is just random analysis. No, it's not random.
No, it's not random.
We're hammering chewing along the fringe of the Cauchy uniform. What we'd like to do, remember, there's two projects here. Show that there's a limit and show that the partition is meaningless. Which partition? Whichever partition is. So let's see if we can all prove together if xn converges to x, then xn is Cauchy.
Which one? Sequence x.
I just wrote it the other way. There's so many ways people writing this.
Okay.
I can do that, or I can do, depending on the book, we do that. So xn trundles off to the limit x. I would like to show that xn is Cauchy. Can we do that? That'd be a good test problem too. Okay, so what should we do first? Well, what do we have to do? We have to come up with a capital N such that if we're given epsilon greater than 0, we must have n of epsilon such that whenever p and q are mutually greater than that, x e minus x q is less than epsilon. Okay. Come on. This shouldn't be too bad. xp minus xq is equal to xp minus x plus x minus x, right? So the triangle inequality is no bigger than, I'll turn this one around, x minus xp, x minus xq. Okay. xn is convergent to x. Is there some way we can make these things small? Let's find n of epsilon, n1 of epsilon, such that x minus xp is less than epsilon over 2 if p is greater than n1 of epsilon, right? So that takes care of one of them. And then by convergence again, there'll be another n such that x minus xq likewise is less than epsilon over 2 if q is greater than his bogey here, right? Well, why don't we just take n of epsilon, the thing we must have. Remember, we must have that. N of epsilon is equal to the min. Oh, sorry, max. Yeah, max. I'm thinking max of n1 of epsilon and n2 of epsilon. Because what's that do? if then, if P and Q are greater than N of epsilon, it means that P is certainly greater than N1, and Q is certainly greater than N2, which means this is less than epsilon over 2, this is less than epsilon over 2, which means that this sum here is no greater than epsilon. In fact, that's strict here. So that implies that xp minus xq is strictly less than epsilon.